Today we want to continue talking about how we measure heat flow and how we relate heat flow to the change in temperature for a sample of a known mass. And the way we do this in the lab is through a specific type of chemistry experiment called a calorimetry experiment, where we set up a physical process or a chemical reaction under specific sets of conditions where we can measure very accurately how the temperature of the sample changes and use that temperature change in conjunction with the sample's mass and specific heat to determine how much heat was absorbed or released in a specific physical or chemical process. And so calorimetry experiments can be used to measure the amount of heat released in a physical process like melting, freezing, or general cooling or heating. And calorimetry can also be used more generally in chemistry, or more often in chemistry, to determine how much heat is released or absorbed by a specific chemical reaction, and then determine whether that chemical reaction is endothermic, heat absorbing, exothermic, heat releasing, and what value of heat the chemical reaction releases or absorbs from its surroundings on a per mole basis. So calorimetry is therefore a general term to describe an experimental approach where you measure what we're going to start calling an enthalpy change, a heat flow change associated with a reaction. And ultimately, in a calorimetry reaction, the amount of heat is always related to the sample's temperature change through the calorimetry equation that we introduced last time. The heat flow Q is equal to mc delta T, where m is the mass of the sample, c is the specific heat of the sample, and delta T is the temperature change of the sample. So if you know the mass times the specific heat times the temperature change of the sample, you know the heat flow in the sample. And so this is a pretty easy equation to manipulate. The key is defining your system and your surroundings correctly and making sure you know the mass of the system and you have the specific heat for the system and you have the temperature change for the system. To do a calorimetry experiment, you need a special laboratory apparatus called a calorimeter, which is a thermally insulated reaction container that you can run a chemical reaction inside, and it's just equipped with a thermometer so that you can measure the temperature change of the system or the surroundings. We'll talk more about how you put together a calorimeter in the next lecture module. But for now, we'll just say you can imagine kind of an insulated container like a cooler that will work as a calorimeter. And all you need then is you need a thermometer that pokes through a port in the cooler to make sure that you can measure the temperature change associated with the process that's happening inside the cooler. So you can think of a styrofoam cooler is your calorimeter. A thermometer gets stuck through a hole in the top of the cooler, and then you have some process going on the inside of the cooler. And if the process you're looking at is exothermic, as the process, the chemical reaction or the physical process like melting, goes on, it releases heat out into the surroundings inside the cooler, but the heat then can't escape the cooler. The heat essentially all has to stay inside the cooler because the cooler, the calorimeter, is an insulator. And then if the temperature inside the cooler goes up, we know that the reaction has released heat into the surroundings and it's exothermic. If instead your process or your reaction is going on and you see that your thermometer indicates that the space inside the cooler is cooling down, you know that the reaction is absorbing heat from the surroundings and you have an endothermic reaction. So basically, just by looking at the thermometer that's in your calorimeter, you can see that if it gets warmer inside the calorimeter, the reaction must be exothermic. If it gets cooler inside the calorimeter, heat is being absorbed by the reaction, and the reaction must be endothermic. So the key pieces of data you take away from a calorimetry experiment is what is the mass of the sample, and what is the temperature change associated with the process. You need the final and you need the initial temperature. And then what you're doing in your calorimetry experiment is you're measuring the heat flowing into or being pulled out of the surroundings. And using the notation we introduced last time, heat flow is abbreviated with Q. So we can talk about the heat flowing into or out of the surroundings. We call that Q surroundings. And we can talk about the heat flowing into or out of the system. And we talk about Q system, heat flow for the system. The idea is inside your calorimeter, like any space where you might run a chemical reaction or run some type of process, the heat flow from your system is equal to the negative heat flow of the surroundings. So if your system is exothermic and is releasing heat out into the surroundings, then the surroundings are picking up that heat flow. The heat out of the system has the same value as the heat being picked up by the surroundings. The direction is just opposite. So don't get too hung up on the sign of Q for right now. We'll talk more about that in our next lecture. But the big idea is that if heat flows out of your system, that same amount of heat has to be picked up by the surroundings, the air or the water that may be inside that calorimeter. And so you always solve a calorimetry problem by saying either the heat lost by the system is equal to the heat gained by the surroundings, or the heat gained by the system is equal to the heat pulled out of the surroundings. If you're talking about a chemical reaction, another way to phrase this is the heat of the reaction, Q reaction, is equal to the negative heat for the solution, the water in which the reaction is being run. The straightforward thing about a calorimetry experiment is no matter which Q you're talking about, Q for a system, Q for a surroundings, Q for a reaction, Q for a solvent or solution, Q is always calculated the same way. It's calculated using our basic calorimetry equation. Q equals M, the mass of whatever we're talking about, times C, the specific heat of whatever we're talking about, times the temperature change. So if you know the mass and the temperature change for whatever you're looking at, and you can find a specific heat for whatever you're looking at, you can calculate the heat flow associated with the process that you're studying inside your calorimeter. So an example of this we'll deal with an example problem of this specifically, is I could take a hot piece of metal that I've heated up somewhere outside the calorimeter, and I could put room temperature water inside the calorimeter. I would drop the piece of metal into the water that's in the calorimeter, quickly close the calorimeter, and watch the heat of the water goes up as the heat flows from the hot metal into the water inside the calorimeter. The idea is because the calorimeter is insulated, the calorimeter retains all the heat in a short term that's coming out of the metal and keeps it in the water inside the calorimeter. So the calorimetry experiment then is if I know the mass of the water and the specific heat of the water inside the calorimeter, which I can look up, and then I know how much the temperature of the water goes up as the metal cools down, I can figure out how much heat flowed out of the metal into the water. And then I can calculate, for instance, the specific heat of the metal as a goal of the calorimetry experiment. So in a calorimetry experiment, we always use a calorimetry equation to calculate the heat flow. And if we know the mass of what we're interested in, the specific heat of what we're interested in, and the temperature change for what we're interested in, we can calculate the heat absorbed or released by whatever we're looking at. And that's the idea of a calorimeter. It's just a special experimental apparatus that's thermally insulated from the rest of the world, where we can study the temperature change of specific phenomena that we might be interested in. Phase changes, ice cubes melting, water freezing, chemical reactions being run, and if we run them inside a calorimeter, we know how much heat is gained or lost during the process.